So in this lecture, I want to continue our discussion of radical reactions of alkenes. And I want to start by talking about the type of peroxide initiator we usually use. That is a type of radical initiator often used. And it's typically a dibenzoyl peroxide. So here's the structure. We have our peroxide being flanked by two carbonyls and some benzene groups. So as you can see, there's this little kind of linkage here, which serves as our ROOR group. This is dibenzoyl peroxide. Now, I'm not sure if I teach a lot of classes, so I'm not sure if I've mentioned this, but we often abbreviate this as pH attached to carbonyls, which are then attached to our oxygens, and then pH, where this pH corresponds with a benzene ring that's a substituent. This is called phenyl. Phenyl refers to benzene ring being a substituent. Again, I may have mentioned that in this class. It's just hard to keep track. At some point, we're going to have to know this, that pH is phenyl. Okay. So that is to say, and the pH just allows me to avoid having to draw a bunch of benzene rings. So when I do my Anti-Markovnikov Hydrohalogenation, which was the subject of the last lecture, got my differentially substituted alkene here, where one side is more substituted, one side is less substituted, and I add HBr to this, but I use dibenzoyl peroxide as an additive along with some heat. I'm going to see this product occur, this product form. Okay, now what I want to do is a similar experiment to this and ask the question, what is the outcome? That is, if this is anti-Markovnikov hydrohalogenation, what if I take the same starting material and apply it to the same conditions, where I've got my dibenzoyl peroxide, but here's a change I want to make to the reaction conditions. I want to avoid the use of HBr. Additionally, in addition to removing HBr, let's remove HBr and use less and less initiator. Okay. Well, now with these constraints in place, let's ask the question, what happens? Well, we have a free radical chain reaction of some type, right? If we still have the peroxide present, I could go ahead and consider an initiation step, right? Because the peroxide's still there, there's just less of it. That's one thing I know that happens is, gosh, that's the weirdest delta ever, but my initiation step occurs where I split the electrons in half that were part of the weak peroxide sigma bond, and I form these benzoyl free radicals, which is my RO dot. Okay, so initiation happens. Well, now we don't have any HBr to kind of provide a source of protons for proton or hydrogen abstraction. It's not proton abstraction because you get an electron with it. Hydrogen abstraction. We don't have any of those around. So what do we do instead? Well, second, we can only thing to do is add RO dot to the alkene. Okay. So we have our alkene, and I'm saying let's add the RO dot, which is my benzoyl free radical. I'm going to turn it around. And now the way we add electrons to pi bonds is we split the double bond electrons in half, where one goes out and slaps high five, makes a bond, slaps high five and makes a bond with, in this case, an oxygen atom from our free radical initiator. The other electron moves over to the opposite side. In this case, we're going to put the radical in the more substituted position because that makes a secondary and more stable free radical intermediate. The oxygen is now bound to the less substituted position. It's sort of taking place of the bromine radical that we saw last time. We still have the benzoyl group attached, which is going to look like this. All right, so that is a propagation step. We go from, even though we have two molecules on the left and one molecule on the right, we still have one free radical on the left, one free radical on the right. So this is a propagation step. Now what do we do? What I want to point out is that we have very little of this around, very little of this free radical initiator around, because I said we're using less and less of it. So what do we do next? Well, what if we add another radical to the alkene? Now in this case, let's consider the alkene adding to the free radical that we made as part of the previous propagation step. So instead of reacting with the initiator radical, we're going to react with the radical that resulted from our previous propagation step. We're going to use the same 3 fishhook arrows. And now this thing is going to get a little cumbersome to draw, to say the least. Here's my approach to drawing it. I'm going to change my benzoyl group to R so that I now have an OR group attached to one end. So I have my OR group, and now I'm going to form a new bond coming up to what is the less substituted position of an alkene, and we put the radical at the more substituted position. So this red bond is a new bond. So if we look, this is another propagation step. We start with one free radical, we end with one free radical. So what's next? Well, we have previously we had a free radical add to an alkene. We don't really have anything else for this new free radical intermediate to do. So I'd say we add another alkene. Let's add another alkene. So let the 3 fishhook arrows do their thing, and we get a very similar structure. We just add another one of these appendages to it. That is, we've got here's our new free radical. Whoops, I have to add yet another group. Excuse me. So now we have, and I should make, in every case, I should make this OR and OR prime so that we separate the R's from the R's and make sure they're not the same. Okay. So I added just a little prime. That's not the part I want you to focus on. I want you to instead focus on the fact that we form a new bond again. And so what we're doing is we're connecting alkenes to what is now a growing radical chain. So alkenes are connecting to a growing radical chain. And so we could do this process over and over and over again. Okay, so we could take our chain that I have growing, and we could say, let's do a reaction with an R group, and 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 on 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 and on, and keep going. Just keep going. Keep going. What is this molecule going to look like? Well, here's what it's going to look like. We're going to have, at the end of it all, we're going to have an RO group, right? This is our initiator molecule. And then that's going to attach to our alkene atoms, right? These atoms are the alkene atoms. I just don't have a double bond anymore. And that's going to attach to another alkene atom by way of this new bond. And we're actually going to repeat this pattern over and over again. CH2, CHR, CH2, CHR, CH2, CHR, CH2, CHR. All right, keep going. How many arrows did I draw? Let's assume I drew a mole of arrows. 6.022 times 10 to the 23rd arrows. Okay, all right, so I got to stretch down here. Okay. Luckily I'm on an iPad, right? So I have infinite paper, but you all don't. This is getting a little tedious. So I'm just gonna kind of draw a straight line like this. I'm gonna put some R groups like this, like this, like this, like this, like this. Okay. All right. Okay, so let's take a second. I need 6.022 times 10 to the 23rd R's, okay? That's all of the alkenes that we added. No big deal. Let's just take a second to see how close I am. All right, so if I count these, I am at, I've got, okay, I forgot that one at the end is R prime. Okay, otherwise I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay. So we've got 2.7 times 10 to the 1 R groups, and we need 6.022 times 10 to the 23rd. Now why? Why would I want to bother with this? Why would I want to keep drawing this? Well, this is organic chemistry. We're trying to draw the structure of molecules. That's what we've been doing for a semester and a half so far, right? And everything on this paper, it's not like 6.022 times 10 to the 23rd molecules. There's one molecule. It's just got 6.022 times 10 to the 23rd R groups, whatever R may be. So I got to depict this, right? Well, it turns out that, what we just do is just kind of just consider drawing a string that just spools around on itself. And we just indicate that, like, if you zoom in on this, this is a bunch of R's. So what I end up getting is like this really long string of spaghetti, right? With a bunch of R groups hanging off of it. Now the size of the R groups relative to the length of the chain is small. And so we're not going to feel these effects. What this is a long chain of carbon with R groups attached. And these R groups are small relative to the length of the chain. Avogadro's number, 6.022 times 10 to the 23rd, is big. I know that insight is worth the cost of tuition today, right? It's a big number, 6.022 times 10 to the 23rd. So they're small relative to the length of the chain. Now what this is called a polymer, and we'll save that for the focus of the next lecture. Okay, so until then, we'll see you next time. Anyway, hopefully that was kind of fun.